Hello everyone, welcome to my presentation. My name is Yousef Heider. I am a research associate at the RWTH Aachen University, and it's my pleasure to give this presentation in the GAMM conference 2021. So the title of my presentation is Suction-induced fracturing in multiphase porous materials, and we have numerical modeling and experimental validation. So suction is a very important topic in different fields of engineering, especially in geotechnical engineering and in soil science. Take for instance the cracks which can be seen in soil due to drying, so desiccation fractures. So drying leads to increase of the suction and leads also at the end to creation of network of cracks, which also very important as they affect the thermo-hydro-mechanical properties of soil. On the other hand, the degrees of suction due to, for instance, to rainfall and to rising of water table maybe also lead to collapse of some slopes. And this can be also seen in some accidents. And apart from like the suction effects in unsaturated soil, we have another kind of suction, which is due to freezing, for instance, soil freezing. This could be artificially in artificial ground freezing or naturally due to some climate changes. And this soil freezing, it leads to change of the suction, so cryosuction, and this also to damage in the material. And this is a topic which will also be addressed in this presentation. So roughly speaking, the aim of this project is first to understand and to predict the suction-induced fractures in porous materials through numerical modeling. We would like also to calibrate and validate our models through conversion with experimental data, and these are on soil drying and freezing. And the methods which we are applying here, for instance, we apply first microscopic analysis just to understand the source of these suctions and these damages. And but we'd like to have numerical examples on the engineering scale. So it's also important to go for the continuum mechanical modeling. And in this connection, we are applying the Facefield approach for the fracture modeling, also the Facefield approach for the phase change material in case of freezing. After this short introduction, I'll talk shortly about the microscopic origin of suction and our way to the higher scale, which is a microscopic approach. So, of course, suction has, as I mentioned, it has its microscopic origin. For instance, take the case of unsaturated soil. We see in this picture the grains and the liquid phase, the blue color, and the air which is surrounding. And we see here the liquid bridges, because this material is found in pendular regime. And we see this curvature between the air and the water phase, and this is due to the interface energy. So to describe this material on the microscopic scale, we could use, for instance, the Laplace equation, which is used on the lower scale. Likewise, if we look at the freezing of soil, in this picture, we see that we would have ice phase and water phase. They exchange due to the change of temperature, and we have the soil phase. But we will see always some kind of water film, which is adsorbed premelted water, and also curvature-induced premelted water. And this is a relatively complicated phenomenon, which can be described on the lower scale using this Clausius-Clapeyron equation. This is on the micro scale, but what about the macro scale? It's difficult to use these relationships directly, so we usually replace these by phenomenological relationships and fine-tuning model, or we use data-driven models with the aim always to describe, for instance, the relationship between the suction, so the gas pressure minus liquid pressure, or the ice pressure minus liquid pressure, and the degree of either liquid saturation or degree of water saturation. For instance, if we look at the unsaturated soil, so we usually use the some phrenological model like Frank-Mushten model, which is simply a relationship between degree of saturation and the pressure head, and we have some additional parameters which have to be adjusted depending on the available curves. And this is a single curve relationship. It roughly describes the drying and wetting processes, but in reality, we have to distinguish between the two curves of drying and wetting, especially if we have to deal with like clay soils with very low permeability. Alternative to this approach, it would be the data-driven retention curve models. The idea in this case is relatively simple. So we have first to generate a database from the lower scale simulation. So lower scale simulations usually they are much closer to the physics, so they are more reliable. We can use the discrete element methods to describe the deformation of our Porous material. And we may use also the Lutz-Boltzmann with multiphase fluids to describe the retention behavior. After generating this database, we can go then to the machine learning. We apply some, for instance, the artificial neural networks with recurrent neural networks, because this is a bus-dependent process. And then we can generate our retention curve machine learning model. The advantage here, of course, we can include a lot of information which are usually not included, for instance, in Frank-Mushten, like the porosity, like the structural tensor, and other macroscopic like information. Now let's focus on the Facefield modeling of drying-induced fracture or desiccation-induced fractures. So the Facefield fracture is used, meanwhile, very widely in fracture mechanics. And the idea is relatively simple. So we approximate the sharp crack or the sharp interfaces of a brittle crack by diffusive one. And this succeeds by introducing a phrenological Facefield variable D, which varies from like 1 to 0, 1 if we have a crack and 0 if we have intact material. And then once we have this, we can define also a kind of degradation. So if we look here at the total energy, it consists of elastic energy and fracture energy. The elastic energy itself can be split into a part which includes the tension and shear, and a part which includes the compression, so that we have a crack if we have tension or we have shear. And then we need another equation to describe the evolution of the Facefield, and we follow I follow in my work the Kinsburg-Lindau approach, which is also widely used. So in this case, for instance, in this equation, it's a time-dependent equation. We could also simplify this if we assume that we have a quasi-static fracturing process. So we get rid of this first term, which includes M, is a mobility or interface mobility. And in this equation, we have also GC as a critical energy and internal link scale. So, and then if we have, because we have unsaturated Porous material, so we have to describe the relationship between the total stress and the effective stress. And for this, we have the Bishop's effective stress, which includes also, as we see here, the gas pressure, the liquid pressure, so the suction in general. And this factor psi can be replaced by the degree of water saturation. So if we want now to consider the crack, so the degradation of stiffness, we multiply a function which is, we call this GD. So this is a degradation function, and it captures the degradation of stiffness. It's multiplied by the part which represents the shear stress, a part which represents the tensile stress. And we have also degradation in the suction, because if we have a crack, then these liquid bridges will also be broken, and then we will have less suction, logically. So if we have a crack also in unsaturated, we have to, in unsaturated Porous media, then we have to take care of other issues like the permeability. So if it's initially assumed to be isotropic, then by the formation of cracks, we will have a preferred flow direction. So we'll have anisotropic permeability, and this has to be considered. as shown in this relation, so we have to first to estimate the crack opening, and we have also to determine the direction of the crack using the ND, which is the norm on the crack edge. And also we can also consider the change of residual saturation. So at the end of the day, so I'll not go into details at this position here. So we have to deal with a number of partial differential equations. in this case of unsaturated Borsmeer fracture, we have 4 partial differential equations, and these have to be solved. We solve this using finite element method. We use mixed method, which includes monolithic solution of the porous media problem. So the first 3 equations. And then in the second step, we solve the Facefield equation. So it's from this sense, it's staggered and monolithic at the same time. I will show in the following an example, an initial boundary value problem. And here we have this domain. It's a symmetric domain, which considers unsaturated clay. This clay is in the experiment is put in semicircular mold, but we simplify this as a 2-dimensional problem. We apply on the boundary also like autoflux representing the drying. So we are not including the temperature here explicitly. And we have some residual degrees of saturation, as you see here. Initially we have no suction. And by solving this, we see the evolution of the cracks is agrees very well with the experiments, from the directions, from the also the way these cracks evolve. I'm talking about qualitatively here, so we do not have the full data from the experiments. These are from the literature. We tested a number of factors which affect the crack patterns, and also we studied the effect of air pressure on the onset of crack or enhancing of the crack. So we see that the air pressure also plays some role. We see that they will have more cracks if we reduce the permeability. There are some numerical factors here, like the internal limb scale of the Facefield approach, and also the mesh refinement might play some role in these patterns. We move to the second problem, which includes suction-induced fracturing, which is freezing. I talked a little bit about the cryosuction at the beginning of this presentation. So now I will talk about what we did in this context. So we have experimental data on saturated soil freezing. This is in the context of the DFG project between our institute and the Institute of Geotechnical Engineering at the RWTH Aachen University. We tested a soil which has this granular distribution. It includes clay, silt, and sand. And as you see here in the geometry, we have insulation on the sides, and we applied like lower and top freezing. But in this representative results, I'm showing the case of lower freezing. So in this freezing, we distinguish between 2 phases. So the first phase is transient phase, where we have ice penetration in the domain. In this case, the cryosuction is not really important because the interface is moving constantly, and it's very much faster than the effect of the suction. And then we have the quasi-stationary state. So when the water-ice interface reaches a certain location, and it will stop there. In this case, it starts to suck more water. First from the neighboring subdomain, and then later from the boundaries. So we applied at the top boundary, for instance, some water source, so that the domain can also absorb water if needed. And we saw that the heave due to this process also increases in the quasi-stationary stage. Also, the interface of the water ice is not really significantly changing. So in this case, we will see some cracks and the formation of what is called the ice lens. We want to capture this effect in the numerical model. So first, we want to capture the formation of ice, so the phase transition from liquid water to ice. And we use here the Facefield approach. This is the original Facefield model, which is used for the phase change materials. and of course, it relies on the phase field variable phi. It changes from 1 if we have liquid phase and 0 if we have ice phase. And then we define this interpolation polynomial. It gives us a kind of mapping between water and ice phases. We can use this interpolation function also to capture the change of density, for instance, or the permeability across this interface. So this is an important issue here. And then we have to deal with the cryosuction on the macroscopic scale. So what we did here, also we relied on some literature in this context. So we proposed a phenomenological cryosuction model. It's very similar to Frank-Nochten model, which is related to unsaturated porous media. And as you see here, S cryo, so this suction, it's equals to the ice pressure minus the liquid pressure, and it includes Xi L. And Xi L in our context is liquid water saturation. So and this is nothing but the phase field variable. So because our phase field variable, it will be 0 if we have ice and 1 if we have liquid. So we can simply replace this in this equation. Now we also don't like to work with 2 variables, so we don't want to use explicitly pressure, specific variables for the pressure in the ice and one for the liquid. So we can get rid of the ice pressure by recalling the net pore pressure formulation, which is given in this equation here. And this originally includes the liquid pressure and the ice pressure, but when we include this, the suction, then we can keep the liquid pressure as the primary variable, and we don't need to explicitly compute the ice pressure because the suction is computed after solving the phase field equation. Okay, so this is for the suction. Now we have seen that in the quasi-stationary state, we have some horizontal cracks, also a crack evolution. So we need to capture this damage effect. Of course, we can use here the phase field fracture model, but we did not use it yet. It's for our future work. So we applied in this preliminary results, some simple damage model, which relies on the phenomenological separation void ratio. So this void ratio is related to the pressure in the domain, and we defined a scalar value of degradation variable d. So that d equals to 0 if the void ratio smaller than separation 1, so we have no cracks, or it becomes 1 if we have like a crack, if the void ratio greater than the separation 1. And it will change in some kind of diffusive way. And by introducing this DE, we can use the same idea of phase field fracture. So we define a degradation function, and we multiply this degradation function by the effective stress of the solid phase, so that our new overall momentum balance can be given in this formulation here. So this problem is a little bit more complicated than the previous one. We have now 6 partial differential equations. The first 3 are strongly coupled, which are the mass balance of the fluid, the momentum balance of the fluid, and the momentum balance of the overall aggregates. And then we have 2 energy balances because we have distinct temperature of the fluid and the solid. And we have the phase field evolution equation. We solve this also using the finite element methods. We use staggered solution. We have to care of some stabilization problem, especially if in extreme cases, like when the fluid becomes almost incompressible. In some cases, due to the freezing, we would have very low permeability. It's almost 0, so it's caused some numerical stability problem. But all these problems have solutions, and I think we could figure this out. Now, to compare our results with our numerical results with the experimental data, first I will address the results for the transient state. We see in this picture here the temperature distribution and the interface, water-ice interface at different times here after 25 hours. Now comparing the temperature time history and the position of the interface time history with the experimental data, it shows very good agreement. Also for the frost heave, we see that we have the same tendency, and we are capturing the heave with some deviation here. We assume that this is because of the like plastic nature of soil, so we do not include here plasticity, and this will be also a part of future work. Now, if we move to the quasi-stationary stage, so after the interface reached a certain position and the crack starts to evolve, our model also could capture this like one-dimensional scenario. And we see here in this figure the frost heave, and the blue line was related to the simulation, the red one to the experiment. It's also giving the same like tendency, which make us also very happy to capture this effect. However, there are some issues like vertical cracks which could not be captured in this model. So that's why we will extend this in the future. So in the future aspects, we want to include or to extend this freezing model to include Facefield fracturing, which use some energetic criterion for the determination of the crack path, so that we could capture also the vertical cracks which were observed in the experiment. We'd like to extend this study of soil freezing to unsaturated porous media. This is also important because there are always some remaining air bubbles in the domain, and we would like to replace our phenomenological models, like for the retention curve, by more accurate data-driven models using, for instance, the machine learning approaches. I would like to acknowledge and thank the support of both Columbia University and RWTH Aachen University. I would like to thank them for supporting my work, and also some funding institutions like the FG in Germany for some funding of the soil freezing project. I would like particularly to thank Professor Bernmarket and Professor Washington and their teams for also the support, and my team also. And yeah, with this, I'm at the end of my presentation, and I would be glad to answer your questions in the session. Thank you so much.